it with you? Okay, let's say I want to compute first e to the power h I1. What is e to the power 0.3? E to the power 0.3? One 1.34?
1.349.
Okay, 1.35. E to the power 0.2?
1.21.
E to the power 0.9?
1.45. 9.
Okay, 2.46. Now tell me, this is 1.35 divided by the sum of all of these. What is that? 1.35 divided by the sum of all these three values. What is that?
0.268.
Huh?
0.268.
0.268. Is 1.22 divided by sum of everything?
0.242.
And 2.46 divided by the sum?
0.49.
Huh?
0.49.
0.49. Okay. So are you getting something what you desired? Let us take another example. So when your h I1 is 0.2, 1.5. What will be your output now? E to the power h I1 and y I1. Tell me, e to the power 0.2 is, I think you already told me this one, 1.22, 1.22. What is e to the power 1.5? Okay. Now tell me, what is the yi1? Hmm?
0.176.
And this one? 7 something. Right? 0.6864. Okay, so something like this. So you're getting what you want, right? The largest HI1 is getting closer to 1 and the smaller ones are getting closer to 0. Right? Okay, so this is what is softmax. Now I have to define the error function. What will be the error function? Error function, I choose it like this. Error function is summation over all samples also, okay. So what happens when you get your yi1 is mostly 0, right? For the other two nodes it is 0. Those terms will go away. Only the one when it is non-zero, when it is 1, that term will only appear. So this will become something like this. Let us not consider S for the time being because we will add it later. Okay, so this one is, so over all I1, only one I1 is true. Let us call that as I1 star. So it is simply log of yi1 star, which is the winner bulb, like the bulb which should be on, the desired one which should be on, right? So this is what it becomes. Very simple. It's a very simple function, right? So this is what is used for classification. Okay, I can write it further that okay, this is minus log of e to the power h I1 star upon e to the power right? Right? This is my error function. If you take the derivative, what you will find? If I take from here, let us consider dou E upon dou W I1, sorry, I naught I1. This will be proportional to 1 upon y I1 star, and then the derivative further terms which are also there in the other thing. So you see here, you do not get any difference function. There is no difference there, right? The yi minus yi hat is not there. This means, let us say you want to make your it should be hat because, sorry. So when your yi star, when yi1 star hat is going closer to 1, your error is not very small, right? It does not make it close to 0. Means your gradient is still a significant value. That is why this one is faster to converge. That is why it gives a better performance, right? So I will just point out. It is faster to converge, right? So this is called, this loss function is called categorical cross entropy. Right? So this is what we use for classification problems. What's the time now? 12. Okay. Now I will pause here for a moment for questions. Please ask questions from today's session as well as previous sessions. E is equal to summation of yi1 log yi1 hat. So this is called categorical cross entropy loss function. So we want to minimize this. Okay. So let us consider this. For the above case, for this case, what is the value of E? Can you compute it? Huh? Pardon? How did you compute that? Huh? How did you calculate it? Huh? Speak little louder. Okay, I think what you are saying is you just substituted here minus log 0.7. That's it. What is the E here? You see this your yi hat is 0. Okay, so this is your yi hat, and your yi1, the desired one is 0, 0, 1, right? So for i1 equal to 0, this is 0, so that term goes away. yi1 equal to 1 goes away. yi1 equal to 2, this stays, it becomes 1 here, and then you get log of 0.7. That's what you also get when you substitute here. Your i1 star is 2 here. So what is yi1 star, which is 0.7? So you get minus log 0.7 as your loss function. And now, what is the value of minus log 0.7? Minus log 0.7 is, so this is log to the base e. Huh? 0.15. Okay, so it is minus here, so plus 0.15, right? Okay, it is 0.15. Let us consider the case when your yi hat is exactly 1. These are exactly 0, this is exactly 1. What will be your loss then? What will be your loss when you actually learn perfectly? This is 0, this is 0, this is 1. yi hat is 0, 0, 1. Sahil? Hi. Huh? Achha. Who can tell? Huh? Why 0? Yes, very good. So it is minus log 1. Log 1 is 0. So it is 0. Error is 0. So that makes sense, right? When this value is, when it actually learns, it becomes 1, error is 0, or the loss function is 0. When this is a smaller than 1, let's say 0.7, then your error is a positive value. When it will be further smaller, then this will be further larger, right? So that's why it is a good loss function, right? When you actually learn the thing, then it becomes 0, the loss becomes 0. When you have not learned, it is greater than 0. And if it is, depending on how better you have learned, it is closer to 0. Okay, so with this, is this question clear? Who asked this question? Okay, is this clear now? Okay, next question. Please ask questions now. First conceptual and then we'll go to coding part. Ask conceptual questions first from any lecture until today. Please ask questions. Don't be afraid, don't be shy. So after last lecture, many people came up and asked questions. So this is the time that when they should actually ask questions, so that everybody can be benefited, not just a few people. Because I'm sure those questions are, most of the people are having the similar questions. So please ask questions. What is bias in neural network? Okay, good question. How many of you have this question? What is bias in neural network? Please raise your hands. Okay, everybody else knows already? Should I call somebody on the board to give the answer? Please honestly raise your hands. How many of you have this question? Okay, so so this is a good question. Okay, so what is bias? So you remember, I will explain it with the help of the previous example, the first example which we considered, that we have two data points. Basically two classes, the roses and the lotuses. right? Now I want to separate it with a line, right? And what is the line? So this was x0, this is x1. I use y equal to mx plus c, so I can say right? This is the line. You remember this example? Okay. Can I analogously write it like this? So I will write it like this. Can I write it like this without loss of generality? So just like I have M and C here, I have got W1, W0 and B here. Is this acceptable? So now can you tell me what is bias? What is bias? Bias is the intercept, right? If I do not use bias, what will happen? Yes, the intercept will be always 0, which means my line will only pass from the origin. Line can never leave the origin. Let me take another pen and explain. So in that case, my line will be confined to something like this. I cannot draw a line which does not pass through origin if I take my B to be 0. Is it clear now? Why do we use bias? Who asked this question? Yes. Is it clear? To everybody else, is it clear now? Who had this question but did not ask? Should we go to the next question now?
Why do we always use sigmoidal function and
Why do we always use sigmoidal function and?
sigmoidal function for activation?
Why do we always use sigmoidal function for activation? Good question. How many of you have the same question? Please raise your hands. How many of you do not have this question? How many of you already know the answer to this question? 1. If you should ask question. Okay, so this question is very important question. So this question was why bias. Next question is why sigmoidal function. Let us go back to our basics. In this case, we assumed to make our classes 0 and 1, you remember we said, let us say this is H. We said this is the side where H is greater than 0, this is the side where H is less than 0. You remember this? Okay, let me take H on the x-axis now, and this function is my y. When H is less than 0, I want my output to be 0. Right? And when H is greater than 0, I want it to be 1. Is this clear? With my classification example, for the classification example, I want my whenever my h is less than 0, I say this is this class. When h is greater than 0, I say it is the other class. Right? So my y is 0 if h is less than 0, y is 1 if h is greater than 0. Correct? So this was called yes, step function, but this kind of classification is called hard classification. Very good. Hard classification. And then we discussed about what was soft classification. So we do something like this. This is a soft classification, right? You remember this? Soft classification. From here we derived the sigmoidal function, and my sigmoidal function can achieve this. And we also discussed that we can have other kinds of functions also which can achieve this. Do you remember what examples we discussed? What examples we discussed? We discussed tan inverse. Tan inverse function can also achieve this. What other examples? I think we did not discuss any more examples. Okay. So basically, you are not bound to use softmax only. We need a nonlinearity. We do need a nonlinearity, but it can be any kind of nonlinearity. People use sigmoid function, tan inverse function, hyperbolic tan function, tan h function, and another popular form of function is. So those who know, they know, but it is not very obvious. So another function is called rectified linear unit. Okay, it's called rectified linear unit. What is it now? So rectified linear unit is this kind of a nonlinearity. H. So it is 0 for h less than 0, and for h greater than 0 it is equal to h. This is another kind of nonlinearity. Now note that it cannot do soft classification, but so it is not used in the output layer, because it cannot do soft classification, but it is used in hidden layers just to introduce nonlinearity there, right? It's a nonlinear function, it's not a linear function, but the good thing is that the derivative is 1 for h greater than 0, and derivative is 0 for h less than 0. That is why it becomes very easy to deal with. And it has some good properties. Like you saw the same example, y minus y hat, that becomes 0 as it gets closer to the desired value. So here similar effect is achieved, that this one stays this derivative stays 1 always, whether it is close to 0 or wherever it is, and whenever it is at the right place, it becomes exactly 0. Okay, so this is another kind of nonlinearity which is used, rectified linear unit, and very popular because of the derivative stuff. Is it clear? So sigmoidal is not the only kind of nonlinearity which you can use. You can use any nonlinear function which is easily differentiable and has some good properties, like differentiability is the most important criterion, and if the derivative stays close to 1 or derivative is not very small, that is very good. More questions? Please ask questions from last lectures or today's lecture. No questions? Okay, so let's go to the next part. Do you have any programming questions now? Programming based questions. Some people asked last time some programming based questions. Please ask now. What are your programming based questions? If you have some assignment problem, you can ask from there. If you have some problem like you're not able to understand how to translate your concept into a program, ask it now. How to debug your programs, ask it now.
What's the need of activation function and which type of activation function we use in the regression program? Which regression type program? Because sigmoidal function is, I think, used in the classification type problem 0 and 1. So in case of regression.
Okay, good question. So your name once again? Chandrakant. Chandrakant's question is that in regression problems, what kind of nonlinearity or what kind of activation do we use? So in classification problem we just now saw, we use, for soft classification we use sigmoidal nonlinearity. For regression, the answer is, if this is your network, these are your inputs x, I, 0, and you have got hidden layers, many hidden layers if you are considering deep learning, and then you have got your output layers. Let's say these are your output layers. Okay. Now in your hidden layers you can use any activation function. Right? Doesn't matter, because you don't need a property that the values should lie between 0 and 1, or the values should lie between -1 to +1. So you can use any activation function in the hidden layers. But the important thing is what activation you use in the final output layer. Right? So for regression, you may use no activation, no problem. You may leave it like that. Or you may use sigmoid also, that is up to you. For regression, you can leave it like that too. For classification, you must use either sigmoid or softmax, things like that. But for regression, you can leave it like that, because you want a continuous value which you can get even without an activation function. Correct? Okay. Next question. Sachin, is the assignment discussed? Assignment 3, which was to use stochastic gradient descent to find the sinusoidal regression, basically. To solve the regression problem, the linear model, using stochastic gradient or using gradient descent algorithm.
Not like gradient descent.
हाँ?
Not like gradient descent.
Not?
Gradient descent वाला नहीं था सर.
पर वो दिया था ना?
Assignment 4 नहीं
Gradient descent वाला assignment last time दिया था ना कल?
नहीं वो नहीं दिया. Assignment
फिर आज क्या किया इन्होंने?
आज इन्होंने
कोई असाइनमेंट नहीं था।